Okay, so today we're talking DSLs. Most of this talk is going to be about building a DSL and in C++ and more. As you can see, I titled the talk After Reflection. There's another talk happening right now called Until Reflection, so I think that's funny. Clearly there's two types of people. So let's get started. So just a few seconds about myself. I work at a high-frequency trading firm. The firm is based out of New York. I recently relocated to Chicago, but you can find me between New York and Chicago at different times. All my time there, I've spent writing C++ for low-latency trading systems and C++ and Python for low-latency, high-throughput research systems. It's been some time. I've been doing both of these. Because of that, I talked about Python and C++ a lot. In fact, this is my 7th conference talk, and I believe I've talked about Python and C++ in each and every one of them. I really like the inherent beauty of programming languages and the fact that you can hide amazing amount of software performance under clean APIs that don't even expose the inner details to you. So that's the most fun part about all of this for me. That's the basis of all my talks, including this one. So this talk is actually a very different pivot from a lot of other C++ talks, because I feel like C++, it's an extremely powerful ecosystem for performance, for compile-type performance in particular, because of the zero cost abstraction principle, which is just paramount in the C++ world, right? And with reflection now, we have this thing called understanding of the code at compile time. This is extremely powerful. We can do the kinds of abstractions that we could not even imagine in the past. This is really powerful. And as I said, we can understand this code now, right? Like, we can understand the code we wrote. The key word is, we can only understand the code we've already written at compile time. And here's the twist. In my opinion, the user's reality, the user of your program, their reality is runtime. It's not compile time. And we often forget about this part of this problem. There's no standard answer to how would you parse code that shows up at runtime. People have talked about it. There's a lot of jitting literature about it. It's just really hard, right? Like, the user wants to express what they want to do at runtime. They're not going to figure out how to compile your software every single time they want to express something, right? And that's the purpose of this talk. Now, of course, this is a C++ Now talk, so discussions, opinions, they're kind of inevitable. This talk is very geared towards that thing. And I guess the core thesis is that DSLs, or domain-specific languages, are not very different from a pretty full-blown programming language, and we should treat them as such. In fact, we should make it easy for C++ to be a system where you write DSLs, and we'll see how that works. Right? So the talk is actually going to start by just surveying a bunch of DSLs in the open source world, specifically in the numerical space, because AI and everything is hot these days. We're going to theorize what a DSL is going to look like in C++. And then we're going to actually build it. To build that, we'll start off by designing a DSL graph, like a functional graph DSL. It's going to have some sort of a function import system, like a foreign function import system. It'll have some sort of type safety. We'll try to target multiple front-end and back-end languages. We'll do everything in C++. We're going to JIT compile this using multiple different technologies. And we're trying to load the result of this JIT compilation in a type-safe manner. That's good. Let's go. Right? A very quick refresher on reflection and how it pertains to this. Reflection is now merged into C++ 26, which is amazing. As of last week, it's also shipped in the production release of GCC. I'm looking forward to trying that. What reflection is, and this code snippet would have made sense to someone 10 years ago. This is not real reflection in C++, but all you want is the ability to operate on code, right? You want to say, hey, give me the class members, and maybe you want to print those, right? This is real snippet. This is one of my favorite snippets from P2996. With reflection, now what you can do is you can get the data members of a class, and you can generate some code. So this code actually generates a command line options parser. something that was actually a very manual process in the past in C++. And the net result of this is that the user can just write something like this. They write a struct. The struct could actually have optional annotations as well. Perhaps they want to add shorthand to some of these. Like instead of doing dash dash file name, maybe they want to do dash file, or sorry, dash f. And this works now, right? And in my opinion, this is a DSL. The struct itself is the DSL. The user doesn't have to write the whole thing. They just express their intent, and we figured out what to do with that, right? We can also parse function signatures now. So here's a function. It takes a double. It returns a double. It has a no except behavior. You can parse out all of this and just print this thing. So we have amazing compile time power now, right? As I said, compile time. You can design compile time DSLs with this. Other languages also have something similar. They just don't have it at compile time. C++ figured it out in a pretty nice way. So like my favorite example, Python, as promised, it's here. You can do crazy things in Python. You can just access the class's layout. You can modify the layout. You can even change what a function does at runtime. Here's an example from one of my previous talks. I have a class that has a copy function. And then I have a decorator called modify class that can just instrument the copy function by adding some prints to it. Simple stuff. It works. You can access this information, but it's all runtime. So is this all there is to this problem? And I think not. I think there's still a gap that we forgot about in this whole story. And that gap is what I call the runtime problem. The runtime problem is that we have amazing compile time libraries. We can actually get code introspection in some way. But for what code? This is just code that already existed in C++. And so a slight pivot from here, right? Why do we even care about this? Because C++ is the bedrock of like modern high-performance software. Well, C and C++ has an ecosystem. So like, as an example, NumPy. It's been around for over 30 years. It's one of the most used numerical libraries in Python, right? People write code in Python. If you're doing numerical stuff, you're probably using NumPy. CUDA, NumPy is written in C. Then comes CUDA. CUDA is written in C++. Of course, everyone knows what CUDA is now. PyTorch, the entire machine learning world has been using this for years. Under the hood, C++ and libtorch. JAX. This is going to be more prominent in this talk. JAX is similar to PyTorch or NumPy. It's kind of a mash of those. It's a Python library. You express the computation you want to do, numerical computation, and it's an accelerator-facing language. So its intent is that it wants to take your computation and run it on a GPU or a TPU for Google's purposes, right? Also in C++, it's called JAX-IR, yeah. Pandas, which is, if you're ever doing anything with data frames and large data in Python, you have used Pandas at some point. Uses Python, under the hood Cython, which compiles to C, C++, and some C++ wrappers. And lastly, there's a new brother of Pandas nowadays called Polars, which sadly is not in C++, as indicated by the RS at the end. But what's common in all of these examples? The big common problem is the runtime problem. The entire input to these libraries is at runtime. The user code arrives late. It's not at the compile time of libtorch, right? We don't even know what kind of inputs the user might want to compute. And the second part of this problem is that even if you knew the code, the specialization of that code for the purposes of the user cannot be prepaid. There's two types of specialization. One is data types or sizes of your matrices. Like perhaps like your code is more optimally compiled if the matrix size is of power of 2, right? It's not always going to be the case, so you're going to have to compile two different variants. The second case is machines. So different GPUs, different families of GPUs, different vendors. All of this cannot be prepaid. Like you can keep multiplying all your variants that you compile, and then you have like a 10 GB .so file that you're shipping with your whole thing. It's not fun. So in my opinion, a host language ecosystem that targets these usages must have a few different fundamental building blocks. Must have an ability to accept computation at runtime after the program has actually started. must have the ability to preserve that structure of that program. So if it's a graph-like structure, it should preserve that. You should have the power to specialize it for whatever target you want, compile it, load and resolve all the symbols that you just compiled, and have a safe callable interface, hopefully typed, for all of this. So at this point, here's a brief refresher for terminology. I've been saying DSLs for a while. It's just domain-specific language. Domain users like to write DSLs. They don't want to write low-level C++ or assembly. That brings us to IR, which is intermediate representation. It's just something that a compiler is going to use under the hood to do all its compiler magic, right? And lastly, there's just-in-time compilation, which, as opposed to ahead-of-time compilation that C++ does, this means that you're actually compiling this thing when you need it, instead of before you need it. All right, so DSLs, right? As I said, I want the user to be able to express their computation at runtime. And oftentimes, as we'll see in the later examples, this computation is going to be more like a graph, where they would express that, do this operation, modify it with this other operand, and so on, right? We want to convert it to machine code, and we don't want to tie the user to compile time. We don't want to teach them compilation every single time. So to drive home this point, let's just look at a few DSLs and how that translates to our end goal here. So the first one is PyTorch. So people write Python code, and PyTorch has two modes. I'm just going to talk about the compilation mode, where people write Python code, something like this, and we actually convert this code to a graph in Python. The how of it is what we'll cover in this talk. And then someone calls a function called torch compile, which is going to convert that graph to something that can be executed very optimally without involving Python during the runtime. Of course, we don't want to be wasting waste cycles these days. You know, people are spending hundreds of millions on these model trainings. So, as I said, graph, right? Here's a syntax tree for that graph, right? Hopefully it's correct, but just to drive home the point, all it does is you take all your operands, you make sure that you're connected to the previous operand's result, and so on. Similarly, JAX. Very similar principle to PyTorch, slightly different usage, and slightly different compilation story. It's the same thing here, where a user expresses some computation. As you can see, they're trying to sum up hopefully some arrays or matrices. They're doing some multiplications, some conditionals, selections. And then they have a decorator called JAX-JIT. So that decorator is going to convert this code. It's going to parse out this code somehow into a graph, and it's going to convert it to an IR called XLA. And then it has a conversion path from that IR back to the machine code. So if you have a Google TPU for some reason, you can actually target the TPU. Otherwise, you target the GPU. This obviously also has a similar looking computation graph. There's a third thing, which I want to contrast with these two things that we just saw. In Python, there's this thing called numba, which is very different from the other two examples. This is actually kind of crazy that it even works. It looks similar. You might notice there's a numba njit. It looks similar to our JAX example. The way it works is crazy. It actually reads the bytecode of Python, maps it back to its internal understanding, and then it writes LLVM code out of it. It's crazy. Somehow it works. It actually works really well, as long as you only write Python and NumPy code. It also has a graph, but this graph has certain other new kinds of nodes here. So it's too small, I think, to see, but there's a loop and a return node. And that gives us a hint that this thing is intended more for imperative purposes, while the previous two DSLs we saw were functional. And lastly, getting back closer to C++, right? CUDA. As a very quick refresher, CUDA kernels are written to do massive computation on GPUs. They're essentially like tiny callables that you call with triple angle brackets like this. The problem is that overhead of launching one kernel and then launching the next kernel with the result of the first one is pretty high. You're wasting cycles. You don't want to do that. You want to utilize your GPU to the maximum. So CUDA invented this new thing called CUDA stream graph, where what you do is you make a stream of kernel calls that happen one after the other. Now the problem is that you're still making the stream at C++ runtime. What if you want to capture the stream, the sequence of kernel calls that you're doing, and just repeat that with different inputs? So what they added is this thing called a graph. What you do is you say, stream begin capture, where you say, hey, you know, right now I'm just capturing the function calls that are happening. I don't want to actually call those functions. Then you do those function calls, perhaps using some existing function you already had, some library function. Maybe you had a parsing function, you were constructing what kernels to call. You just call that. Then you end the capture. And with this captured stream, you can actually initialize a graph object and then call it later whenever you want. So this is some sort of a graph capture in C++ at runtime. It's kind of painful. But to be fair, it's still less painful than having the users write out a graph themselves. Like, you don't want to teach people how to create graph nodes and connect them with pointers and data types, right? So it's still better than that. So why are we talking about all this? So my hypothetical example for this is, imagine you have a bunch of scientists working in a lab, and you want to give them a simulator. That simulator ideally wants to run whatever they want to do really optimally. You don't want to incur the Python runtime overhead there. And perhaps you even want to be able to give them more tools than they would have if they just wrote this thing. Maybe you want to understand this thing, give them a visualization of what stage they're on in their simulation and so on. Perhaps you want to give them profiling tools about all of this, right? We really need to be able to understand the code a user wrote to be able to achieve such things. Similarly, it would be nice if you could do the same thing in game dev, perhaps. That's just another hypothetical example, right? Not everyone in game dev wants to write C++ and recompile the entire game engine, right? So that brings us to the target code that I have for this talk. The purpose of this talk, the code looks tinier than I expected. What I have here is just a state estimation problem from autonomous robotics. I just found some equations on Google. And here's some hypothetical code where all that's doing is just conditionals and matrix multiplications, transposes, and a few other such numerical operations. It's also happening in a for loop in C++. Maybe we're doing it n times. Wouldn't it be nice if we could just write this code, perhaps in C++ or in Python, and understand everything about this code? Perhaps even inject things like profiling metrics on that. Like maybe someone ran that code and they want to figure out, hey, it's running slow, which operation is slow? And all they would have to do is just flip a Boolean that says instrument matrix operations, and they could get the time taken for each of the matrix operations along with the source code number. It would be nice, right, if we could do that? So this is the goal of this talk. We'll build this DSL. To build this, what do we need? The first thing we need is actually, how do we parse this computation graph out? Because we don't have parsers right now. The first way to do it is to use reflection-style DSLs, have the user write a struct or something like that, like we saw with the options parser. Maybe not the best idea. It's too limiting, I believe. You could ask the user to write some DSL in some .abc new kind of format. Then we would convert it to C++ as a source-in step. Then you link the source-in into the final program, and you run that. You also have to teach the user how to build this whole thing, and your source-in might have other dependencies, and now you're stuck with teaching the user how to build your toolchain. Not super fun. The second part I want to talk about is a refresher. Let's say we actually did do the source-in thing. We still need to parse whatever code the user wrote. And in my experience, at least, it's not fun. During my undergrad, I actually wrote a compiler for Go at some point, and the best lexer available back then used to be Flex. This is how you write lexer code. I don't know about you, but this makes very little sense to me 10 years later. This is how you write a parser in Yak, which was, well, I think there's another one called Bison, but it's one of the two big parsers that were available back then.
I wrote a generator for C++. You should use mine. It's much better.
Okay. So that's good to know, because this is not fun, and it was not fun when I wrote it back then either. So, as I said, it's not easy. It's not super hard. You can learn how to do this, but do we have to? I guess the second option is runtime, right? We can ask the user to express all of this in JSON, so we skip the whole parsing problem. But JSON is, of course, still limiting. Or you could invoke the flex and yak toolchain at runtime, which, again, is horrific. You could read an input file where the user provided that JSON to you, and you could create a runtime graph of operations that you want to do. And at that point, you're paying virtual function cost, because everything is at runtime. So I have an alternative. What does Python do here? Because we saw a bunch of examples that seem to be doing something similar, right? So let's call it Python time, where we have a C++ library. You bundle it, you ship it however you like. We provide Python bindings for that library, and the user's Python code is somehow constructing a graph for us, the graph of Python objects. And we try to interpret that user's graph. So this is great because we skip the lexer and parser, right? And we can compile it to an IR. Maybe we'll use LLVM, some other thing, XLA, MLIR, anything, right? Nothing needed. So this is great. We solved one part of the problem. We left C++ in the ditch. We didn't talk about it at all here. It kind of worked. So just as a comparison, the only big difference that showed up here is that Python saves us from parsing. So my hot take here is that the traditional design of DSLs in C++ often pushes us towards this parser work, right? And that becomes technical debt. It's just something very specific to your use case. Python is already a DSL parser for us. There's so many DSLs in Python. I think we should just borrow Python's idea of how to parse DSLs, port that idea into C++ and mainstream it, right? So that's what we'll do. There's a side benefit of doing all this is as long as you don't tell people to write JSONs and they're writing C++ and Python, they can actually inherit their editor. They can do jump to definition and all of that. They don't have to make new tool chains to be able to understand primitives in their editor. So the second part that we didn't talk about earlier is the execution. So how do you execute these graphs that we've computed? Idea one, you make a precompiled list of functions, and these graphs are just calling those functions with whatever runtime language you have. And the idea two is dynamic dispatch. So dynamic dispatch is you take a bunch of these functions, you compile them into C++, you expose them as Python wrap functions to the user, and you execute them sequentially in Python or whatever. This is how NumPy works. It's the oldest idea, it works great, right? Unfortunately, if you're doing the same operation over and over again, as people do with machine learning as an example, you can't really jit this thing into a flattened machine code, right? Unless you're using Java. This is one of the good things about Java, because if you just do the same thing over and over, you don't pay the cost again. I like that. Unfortunately, we don't have that in C++. Secondly, you kind of leave cross-function inlining and optimization and deduplication opportunities on the table. So we had absolutely no place where we could do that, because if the user called the same function 2 times, we have to run it 2 times. As an example, to drive this point home, here's a random machine learning-ish workflow where someone says, if you want to use ReLU, then you do that one operation, otherwise you do the other. You have a bunch of C++ control flow operations here. You have some optimized functions like multiply, scale, add, etc. And you might notice that there's a duplication here. I'm multiplying the same 2 matrices in 2 different places. And we have no opportunity to actually take these 2 functions and merge them into one if you're running C++ here. So you can't precompile the graph here, right? Because if you had to, you would actually have to take that previous function, specialize it for both those booleans, and ship those 2 things as template arguments. So we don't want to do that. Of course, the user's computation itself may be so dynamic that you can't even enumerate all these functions. And as we talked about, the target architecture is not even known at the compile time. So as we get closer to the final build stage, my hotter take is that runtime DSLs are just programming languages. We're doing all the work. Let's treat them as such. Let's build a programming language, right? So our programming language is going to have users author some code at the process start. We're going to capture the graph in C++, We're going to do some runtime specialization and deduplication. We're going to compile it to some machine code, and we should get some compiled functions back that we can call, and hopefully profile automatically for zero cost. So all of those are very vague. Each of those things has multiple options. I'm going to try to cover most of those high-level options in this talk. The first option is that the user code could be written at compile time in C++, hopefully. No parser needed, that's our goal. Or the user code could come in at runtime from Python, perhaps. We want to be agnostic to it. The second variation is the backend. I don't want to be tied to a backend, so we want to be able to lower whatever computation the user wants to multiple targets, like a GPU, a CPU, in different ways, perhaps, with different IRs. So what we need to build for this, the first thing we need to build is a graph DSL. We'll build that. It should look like all these other examples we saw earlier. It should have some symbolic values. It should even be able to track where a node was created, maybe even have some types. The second thing we need is a compiler stack to be able to compile that into machine code. And the third thing we need is dynamically being able to load those modules that we just compiled. I really care about type safety, so I do want to validate ABI here. It's not essential, but it's important, I think. All right, so let's abstract all of them and build them one by one. Just as a visual, this is the same thing we talked about. We could have multiple inputs. We convert them into a graph, and we convert it into some IR. I apologize for the tiny font on this one. The IR is something that can be serialized to disk optionally, and it can be jet compiled to a target. And lastly, the jet compiled target can be loaded as a runnable function. All right, time to start building. Let's make a graph of user code and user intent. So we'll design a DSL. Maybe it can be type erased. I actually ended up doing a typed DSL, but it wasn't the most critical part of this thing. Maybe we'll try to target every DSL a user can think of. That's probably too optimistic. So maybe every numerical DSL. There's a benefit to having a single-ish DSL that you parse, because it gives some sort of a uniformity to the parsing thing. You can build this once, and you can target multiple use cases, perhaps a game dev, perhaps a software developer, perhaps a scientist, the examples I had earlier. We don't want this DSL to be targeted to certain function languages and, some function libraries and things like that. It obviously has some con, which is that if we don't define the DSL's function spec, someone will have to define a dialect of this DSL where you actually give meaning to, okay, how do you do matrix multiplication in this DSL? You might also lose some of the intent that the user could have provided to you if you had a more specific DSL. In this talk, I end up going with a very general DSL with a very specific dialect for matrix multiplication and matrix operations. One doesn't have to do that. That's what I ended up doing. All right, so let's get the user to write some LLVM IR. Of course not. That's too low level, right? Like, we need something better. So this is what I would like. The font, again, is a little tiny here. What this says is that there's a Python function saying custom runtime func. It's supposed to consume 2 nodes. It's supposed to read from a file what to do with those nodes. And it's supposed to apply some function on those nodes at the end. So the read from the file part is pretty dynamic here. This cannot be known at compile time of our program. I would also like the same thing to work in C++. This is the exact same code, no change here. I just replaced the for loop in Python with the C++ one. The third thing we have is I would like to have some sort of a foreign function interface where you can perhaps do some sort of an import like this. You can say, hey, import this function using reflection perhaps, and call that function as a part of your graph, but you don't want to call that function right now at the time of building this graph. This function specifically here, DGMEV, it's a double precision general matrix vector multiplication. Very common, in the terminology comes from this interface called BLAS, which is basically linear algebra subprograms. a lot of this talk is going to use some BLAS functions wrapped through CBLAS, which is the API I'm using here. So how do we parse these graphs? And the approach I have here is called tracers. This link is from JAX. They call it tracers. And the idea is that if you have a function and you put a @JIT on it, what you want to do is you want to parse the function's body. You don't want to actually run the function. So if this code was run, where we pass in two random numbers to this function, those prints would actually not print those functions. They would print something else. They would say that these x, y, and result values are actually something called JIT tracer.
May I ask a question? I'm somehow
Yes.
losing track. So you parse graphs, but why do you parse graphs? Why do you not have a specialized representation for graphs? You have a data structure for graphs. Why is there any parsing at all?
There's essentially no parsing, yes. There is a data structure. That's the trick here.
Okay.
Yes, yeah. We don't want to write parsers. Yeah, and the approach is tracers, basically, where you don't want to parse graphs. What you do is you inject a tracer object through the function you want to understand, the function you want to introspect. The result of that function, actually, will also be a tracer. How would you achieve this? Obviously, with operator overloads. Because what you do is you define that adding two tracers returns a third tracer, which records the computation that was done as a part of the earlier add operation. So the way it works is the inputs are proxy values, as I mentioned. To your function, you actually pass in proxy values. The output is a proxy value, which should capture what you just did. So if there were any file reads in between, they should happen at this time. So maybe a file said that you must add, not subtract. So that's what would happen in the output proxy value. Any arithmetic or function calls should create new proxy values. Of course, not every function is going to be able to do that, because not every function would know that it has to be given a proxy value as input, and not maybe it's trying to do a comparison with 0 for one of the values. So what tracing is basically evaluation over symbolic values. That's all there is to this. So this is a practical answer to a parsing DSL frontend. So there's no graph parsing anymore. It's just execution. As I alluded to earlier.
So I have a question. If you want to obtain these data flow graphs, you need to do what's called a layers analysis, and that's quite complicated. Are you somehow considering that?
No, it's very simplistic in the sense that
these are languages without aliasing.
Yes. It actually would have alias. Actually, it would understand aliases, right? Because at runtime, the aliases should get resolved.
Because you're somehow discussing how to build a compiler, but that's actually very complicated, and you're skipping very much of that.
If you're talking about duplicate nodes, that would come up later. I do have a slide about that. So the simple part here, this is the simple part, of course, no fancy compiler stuff here, is you do some operator overloads. You define that if you have a graph node, and you add two graph nodes, you get a third graph node. Simple.
And there's also things like type checking. And
yes, there's something about that here. Yeah. So right now we're just talking about capturing what the user said instead of actually interpreting it and converting it to machine code. So you add operator overloads. You can add some method calls to this thing. And all we did right now is just capture what the user wrote, nothing else. We didn't do any type checking here. We can add some expressions. We can do some function calls. And here's a function call. It's the same call that we saw earlier. All this does is just build a graph node. We don't have any capture information here about we haven't started parsing this information yet. We can do some conditionals, like here's a where conditional, where we say that if that proxy value's result is greater than 0, then you select the left-hand side branch or the right-hand side branch. We also have some sort of C++ control flow, where you have an if condition, but this is a C++ if condition. It's just regular C++ looking code, but right now we're not running any of this code. Option 2 in this is you can literally convert the whole thing to Python. You add Python bindings to construct these nodes, and you get the same thing. So so far, we're language agnostic. As you just saw, we can just parse out complicated things. All we get out of this is some sort of a IR-ish printed thing. Like, I didn't try to I'm not using this thing. This is just how LLVM ends up printing their IR. So you can parse out all the nodes we just constructed. There might be duplicates here, there might be aliases to nodes here. We haven't captured what the user intends to do with memory management of all of these things, who manages the output of the whole thing, and so on. We just have a graph. We can also capture some reflected function calls. So perhaps a user wants to call, on the left-hand side, this function called confetti, which is in their C++ code. We can parse it out. We don't have to use it yet, but we can put a node in there which says, hey, there was a function called confetti. It had this signature, because now we can parse signatures of functions using reflection. And there's a graph node for that. We don't really have to do anything with it yet. There's some limitations here. The control flow cannot depend on traced values. So this if happy path, like the happy path object cannot be a tracer or a proxy value here. Any external calls must be bound by something called effects, which is not very functional, but that's how functional languages are. So about effects, the simplest solution to these problems is you expose a syntax, or you expose a convention where users have to pass their state into your function as a parameter. And that's how most functional programming languages get around effects anyway. So, why even keep this graph in C++? Right? There's multiple answers. One of them is just that now we have a reusable internal boundary. We have something that we can use for multiple purposes, for multiple backends. We're also agnostic to the front end. So we can either be writing Python or C++ and construct the same thing. So if you end up writing a converter for this graph to GPU, it's reusable in both. Could we have used any other IR for this thing? I think other IRs are definitely more powerful in a way that you express more intent in them. You express where a computation's memory allocation must happen and things like that, right? The goal of this was for users to write domain-specific code. So my personal goal was to not get into that story. So just to take a look at some other IRs, here's the IR behind JAX. I like their statement a lot. They say not all Python programs can be expressed with this IR, but turns out many scientific programs can. It's great. Unfortunately, the IR is too low level for users to want to write. Then we have MLIR, which is a project which has a very similar goal to this talk. They say it very nicely. They want to build reusable and extensible compiler infrastructure, and they want to address software fragmentation around the compiler infrastructure world. That said, sadly, the IR here is also too low level for users because you still end up defining memory management and everything. So these other IRs, they're not often meant for writing by humans, right? Like you lower them from Python and you forget about C++ because why not? And what we're trying to do is just capture a user-friendly intent here, that's all. So we don't really need any advanced compiler dev at this stage here. It's simple but lossy. And the main goal is, what do we want to use to generate the final IR? And we don't want to fall into this trap, of course, of this XKCD comic where we invent a new standard and you get the 15th standard instead. Okay, so we have this IR. We're going to put a pin in this. We've deferred compilation to the next stage. That's task number 2 of our problem here. The good thing about this is the user keeps their editor, as I mentioned earlier. So if someone is writing this IR, they don't have to. They get jump to definition. They can call their usual C++ functions. They get their type checking. They also don't need to relearn operator precedence because I forgot to implement it the correct way. You know, it happens. Different languages have different operator precedence. Different languages have different regexes. We don't want to fall into that trap. So I think what we have is decent. It's not imperative. We didn't add any loops yet. We added a bunch of expressions. We didn't tie ourselves to any backend. We tried to support capturing function calls at least. So speaking of external functions, a very brief note on those. I do believe that external functions being supported in DSLs is pretty important because otherwise you end up reinventing a lot of things. Like in this case, I have an example where it's just trying to call a global function on some of the results. Maybe you know that the result is a matrix and you want to call a matmul on it. you could expose external functions as first-class top-level functions in your DSL Python bindings or something like that, which is a valid approach. At that point, all you do is you make your graph language a bit of a dialect. That's all. Okay, so now that we have a graph, now we need to convert that graph to some machine code, right? So this is where the actual compiler dev starts. So also this is the hard part, right? Like, not only do you have to do compiler dev, you have to figure out what's a good IR compiler, how do you package dependencies, how do you customize or how do you cache the result of that compiler, which obviously never has a good answer, and how do you customize this thing for runtime? We left all of these hard problems here, so let's try, right? So I have like two different types of possible solutions to this. The first possible solution is we lower this DSL to a specialized IR, and then to machine code. So it's easier because you're reusing a specialized IR's infrastructure. That said, I had to learn a new IR for this, so the first thing I did is not that. I did something else, which was very tempting. I converted my DSL to C++. It's very tempting, and I thought, okay, let's try, let's see how it works. And in this case, if you look at these two lines that I have, C++ becomes our specialized IR. And the IR compiler is just the C++ compiler. So the first draft is what we're going to do is we're going to iterate over the graph of our nodes that we just constructed. We're going to deduplicate that graph so that we don't have any nodes that are the same. We're going to generate C++ code to execute each of the operations on those graphs. And we'll let the C++ compiler deal with half of those things that we just didn't want to deal with, like dead code elimination. Perhaps there's a condition that never gets set to true, maybe register sharing while trying to not create too many temporary variables into different registers, doing some sort of vectorization. If the compiler can do it, our language can do it. Simple solution. Ugly answer. Doesn't look great. Of course, this code is just stringification of what you would want the final thing to look like. It's a string stream output, and I'm just pushing all the things I want into it. This is the header. This is not even the body yet, because we have to do input and output management. No need to read this code. It's not meant to be read. The approach that I took to actually generate this is going to get carried over to the rest of the talk. And the approach is that while constructing or rendering the C++ function, I maintain something called a context. This context has maps from the node ID, so each node has a unique ID, to certain runtime values about that node that we discover as we parse the nodes. The runtime values could say things like, what type of node is this? Is this a scalar node or a vector node? How many dimensions does it have? If we know the type of this thing, if we know the length of this vector node, things like that. So the second thing is what I was just showing here. I have a few different hard-coded types in this graph at this moment because this is the first draft. And then we write a function called lower numeric to C++. There you have a graph, and you have a bunch of input nodes, and then you have a bunch of required function imports. So the way it works is I'll initialize my vectors and these maps that I just described for my input nodes and the output nodes. Then, while we loop over the nodes in the graph, what we're going to do is for each type of node, we have to do a different thing. So one type of node is a literal node. Literal nodes are very simple because all you do is you assign it a value. You say int node1 equals 1, whatever literal that the user has passed in. So that's on line 33, which I don't have a highlight on, unfortunately. But all we're doing is just literally printing this thing out. We'll let the C++ compiler duplicate all of these temporaries. The second thing is for binary operations. This is not much harder. You can just say int node5 equals node3 times node2. And the way you do that is all you need is a way to represent this previous node's value as a reference. And that's why we keep, every time we do an operation like this and we render a new graph, we update the context that we had, which represents how to talk about node 5 in the rest of the graph. And since the graph is topologically sorted, because you know the dependencies of all these nodes, everything works fine because you're only discovering nodes. You discover nodes before you actually use them. So putting it all together, you can start by validating your numerical graph. At this point, you can do some sort of type checking. You can do some sort of deduplication. You can find out all the function imports you need. You can lower this graph to C++. You can compile it somehow. Now this somehow is very simple. There's just I'm writing a C++ file and calling clang on it. You can DL open this thing. You can load the symbol. And you can do what you want at this point. I did add a second step here where I pass in the imported functions as well. That's just a detail here. And it works. You can call this thing. I pass in a bunch of input nodes. I create a graph where I'm calling some myfunc on these things. I'm compiling this thing. I run it with some specific vectors as input that are converted to spans. The whole thing works. So this is the simplest version of a DSL compiler. The situation is that we need a C++ compiler when you actually run this code. It's not great. You have to manually import, export symbols. You need a file system. Someone once told me that C++ doesn't acknowledge that there's a file system, so you can't standardize things that need a file system like this. But it works so far. So maybe there's something better. And there is. There's a much more standard solution to this jitting, which is called LLVM org. This is only for LLVM targeting architectures, but it's great. So earlier, what we were doing was hand-rolling our compiler. LLVM org, on the other hand, org stands for on-request compilation. It's a production-grade JIT backend. It does lazy compilation if you need it to. It does runtime symbol resolution properly for you. And most importantly, it gives us structure. We were doing ad hoc things in the past, and now we were doing things like, somehow compile to disk, DL open, cache these things. LLVM org is just a nice interface, and it's all in memory. This is the solution that I really want to play with here. So at a high level, it has this thing called LLJIT, which is just the primary object that you interact with. LLJIT owns the JIT stack in memory. It's going to accept the IR in multiple different possible forms. It's going to materialize that IR to machine code. It's going to do all symbol resolution for you. And perhaps someone has heard of MCJIT. That's a 10-year-old thing. This is what now replaces that in the LLVM ecosystem. It's the simplest possible API for jitting. So before we get into the code, I wanted to draw a diagram. I did a crappy job of doing that, and then I gave the diagram to AI, and it generated a much better version of it. It looks nicer, it has nicer colors, so I'm just using this one. So at a high level, the way it works is in LLVM org. You make these things called JIT dynamic libraries. Each dynamic library owns the code that is supposed to be rendered to the machine. And obviously, the code would have some symbols, but that doesn't have to show up at this moment. Dynamic libraries can be added to your jitting context, your LLJIT. And the order in which you add them is important because that's the order in which they would get loaded. So if you have symbols in dynamic library 1 that are used in 2, you must add them in that order. Now, the second question you might have is, how do you inject code into this dynamic library? So they have an interface for this called a materialization unit. There's multiple possible ways to do that we'll see. And for each materialization unit, you can attach something called a resource tracker, which provides you some sort of a garbage collection, so that if some part of your code is no longer used, you can actually remove it from this whole ecosystem of JITted code that you have at runtime. So task 1, how do we write this IR code? And to do that, you have to build something called an LLVM module, which has a C++ API, luckily for us. We're going to take that LLVM module, we're going to wrap it as a thread-safe module, which is the class that this system uses, and we'll add it to our just-in-time compilation dynamic library. The interface for that is pretty simple. All we have to do is create this thread-safe module object. You could also take your precompiled LLVM object code and add that into this thing. We are not going to do that. We will just build it in C++. There's other advanced APIs. If you want to do LLVM source-in on demand, if you want to implement the actual low-level interface on your own. So we won't do that. We'll do the simplest possible thing. We'll use this as the default in-process backend. We're going to convert the graph nodes to LLVM IR. And we'll let this org system handle everything for us. We're targeting LLVM. We can swap it out with something else, though. Users don't know about this. And they're just expressing intent, right? We'll do optimizations here. So how does this look like? The first thing about building LLVM IRs is you have to start by creating something called a function, obviously. And functions always have, functions are built out of these things called blocks. So each LLVM block is something that must have an exit statement, that's all. All the other statements in the block must be non-terminating, and then at the end there must be a terminating statement. That's what this is the API for building code in LLVM. So I'm building a block called entry. I'm going to add some loads into it. I'm going to add some comparisons, additions, divisions, selection, instructions into it. This is just some hard-coded graph here, some store, and then a return. And that's it. This is how you write LLVM code in C++. Of course, this is very specific. So to do our whole compiler here, what we'll do is we're expecting that somehow we'll convert our graph into LLVM code instead. We're going to create a dynamic library. Inside that dynamic library, the first thing we will add is an imports module. The imports module currently has nothing, but since this has to be added before the source code, we'll just add it here right now. The second thing is whatever lowered IR code we have, now we're going to add it into our ecosystem after the imports have been added so that the ordering is correct. This stage, you can bind all the imports because you know which functions are used by your system. And at the end, all you do is you ask LLJIT, hey, I must have given you a function called graph_DSL run. Can you get that function for me? I need to use that. And it's going to compile everything in memory for you. We don't have to think about it. You just get a pointer out of it, that's all. You can call that function, and it works. So to build the actual function that we saw, we start by creating a module. We specialize this module for the target triple of our target machine. Target triple means architecture, vendor, operating system, and environment. So all of these things, LLVM just provides it for you. There's a public API to get this. You can get the data layout on the machine, what kind of pointers there are, and so on. You can get these pointer types as C++ object types here, because right now we're constructing LLVM code in C++. Then what you can do is you can actually make the functions that we just saw earlier. This is just repeated code. You make the entry block, and now we need to fill in the rest of the whole thing. And surprisingly, the filling in code looks very similar to what it looked like when we were writing all the C++ source encode earlier. I'm still keeping that context object. I'm still looping over all the graph nodes. It's just I'm not rendering some unnecessary things this time. That's all. So we can handle input functions. We can handle literals. We can handle binary functions. Binary functions are slightly interesting because if your inputs are a vector, I wanted to handle vector types here and not just scalar types. We want to emit some sort of like a loop, right? You want to do some operation looping over a vector that you got as input, perhaps with a dynamic runtime, dynamic size, right? So what you do is I made a function called emit index loop, to which you provide a lambda, and the lambda will be called for every single iteration of the loop. And as an input to the lambda, you get something called an index, which is the element index. So this part is pretty simple. Now, the only thing we're left to implement is the emit index loop. And as you notice at the last highlighted line, I have a store there, which is just one of the LLVM instructions you can call inside the lambda now. Similarly, you can implement conditionals and function calls, and we're going to dig deep into those now. For emitting index loops, it's actually interesting because what you have to do is, how do you actually render out a loop body? The first thing you have to do is you have to check the loop condition. You need to have an exit point in your loop. And what you want to do is you want to tell LLVM that when you start the loop, the first thing you do is go to the start of the loop. Then you check the condition. If the condition is wrong, you jump to the end. Otherwise, you run the loop body, right? So that's what we're going to do. We'll build a branch. We'll tell the LLVM thing, hey, just branch to the header, go to the header. And now whatever we're going to be writing is going to be, we're going to add the insert, we're going to move the insert point to the header building block that we have. Inside that, we're going to add a phi node. A phi node is a special node. This is an LLVM terminology. This node's value depends on how you got to the node. So this phi node has two entry points. The first entry point we're adding to it, index arrow add incoming. We're adding an entry point saying that if you enter from pre-header, which means you entered from the first time you got to this loop, the value of this node is 0. So this is how you write LLVM imperative code in a way. So then what you do is you say, hey, here's a node that represents, is the loop active? Is your loop condition still valid? If it is, then you create a conditional branch node. You move the insert point to inside the body part of your loop, and then you call the lambda that we just saw. So if you call the lambda, everything works. At the end, you can add index add incoming, and that's just going to move add the second incoming edge into the phi node that we saw earlier. And at this point, we're saying, okay, this is the second way that you get to the loop. At the end, you exit, and that's it. The fun part of this is you can actually do 2D loop rendering pretty easily with this. All you have to do is just call this emit index loop recursively, one inside the other. And now you have an emit 2D loop. Similar to this, we have conditional rendering, which is not very complicated. You just parse out the nodes that you have from the left, right, and the condition. And then you generate a select condition in LLVM using create select. That's it. If you have a vector conditional, then you can render an index loop for that thing. Binding imports. We didn't talk too much about symbol resolution because it's pretty simple with LLVM orc. You can actually just, it can give you a mangle lambda that you can use to mangle the name of any function you have in your ecosystem. It's going to mangle it, and all you have to do is provide it a map saying, here's a symbol map. If you see this mangled name, this is the pointer you're going to call. That's it. The end result, I have some toy code here, the kind of code we started off with. And this works. Like, you can run this on C++ now. You can do all these matrix multiplication calls. You can do the conditionals, C++ code, and all of this works. The fun part, this is the big win, is that since our code understands this computation that we just did, you can actually flip a switch and add profiling to your code. So that's exactly what I did. If a Boolean is true, I actually told the LLVM lowering code to also inject certain other instructions right before and after every function call. And that's great because now I can actually look at which function call is taking more time in my code. And as you can look at this example, if it's visible, all the matrix multiplications take something like 70 milliseconds total, and the transposes take 13 milliseconds total. But that's just because there's a different number of calls happening there. This is super useful because this is something you cannot do if you write non-DSL code. Because if you write eager code, that's just going to run, and you have to ask the user to add profiling code to their own code. Here it took a single Boolean. There's no effort involved. So summary, we're able to JIT a DSL to machine code. We're able to access any functions we want to expose. Is that all? And so this is where I ended up doing a very surprise experiment, even for myself. So I have an Apple GPU at home. I thought, why don't we change the DSL's backend to be a GPU now? And how hard would it be? So turns out not much harder. So Apple GPU has this thing called MPS graph, where MPS stands for Metal Performance Shaders. That's just Apple's ecosystem of writing C++ code. And what you can do is you can just define a bunch of examples, which I did for myself as a goal. I said, I want to be able to call these matrix operations in Python. They should match the operations that would have happened if I JITted this to C++ or to the GPU. So if you notice, all I did is I changed the decorator on the function from CPU to GPU. I also wanted parity between C++ and Python. I wanted the code to look the same. So this is the goal of this task. And we can do that. So now we have a DSL which you can feed into it with multiple input front-end languages, and you can get multiple backends out of it. Of course, asserting the parity is not the hard problem. All you do is you construct the graph. Here's the graph I constructed. I'm just doing some matrix multiplication. And you assert that it matches by compiling it for the CPU and the GPU one by one. Simple stuff. And behind the scenes, the code will look very similar with certain funny primitives in there because this is Objective C++. MPS graphs gives you a message passing syntax for Objective C++ to be able to call, as an example, this line here, add with primary tensor. That's just one of the ways to add things in MPS graph. And yeah, this works. Like all we did is we took the same code we had earlier, but we replaced the functions, the LLVM functions with the Apple functions. And just to give some evidence that all of this works, like none of this code is different, by the way. Like it's just same thing, different syntax. It's Objective C++ syntax, which I did not know and I had to learn for this thing. It works. And
so what is Objective C++? Is that a dialect?
It's Apple's variation of C++. And honestly, I was very surprised. It has a weird syntax like this. Everything is an object somehow, and you do message passing instead of doing structured object-oriented programming. It's funny. It has runtime dispatch for functions. And the code is very unreadable to me. I had to ask AI to explain how to write this code multiple times. Apparently, the first argument is not named, but all the other arguments are named and things like that.
When I see something assigned to a pointer, I immediately get afraid. I don't know what is happening.
Yeah, I have no idea what's happening on this one either, by the way. But that pointer is actually a NS object pointer because everything in this is an object.
It's a smart pointer.
Good question. I don't know. I think it has runtime garbage collection from what I remember, but if someone who knows more could correct me here. This is the first time I wrote Objective C++ as well. The file extension is mm, which parts of it, yes. Yeah. It works though. I actually got all my tests to pass on the GPU code as well. I had all these tests on CPU as well. And why does this matter? Because now our graph is not really like specific to any specific IR. It's just different optimizations can be done on the same graph, and you can target different backend architectures. And this is exactly what a good graph DSL should do, right? Different backends, different frontends. To drive home the point, I have the target example that we started with. It's a dynamic state estimation problem. It has a lot of matrix multiplication operations. We're doing some sort of a future prediction by using the sensors on a robot. We know some sort of covariance of the error of the sensors, and we're trying to predict our future state and the future covariance. Lots of operations. At the end of the day, the C++ code that we want to target should look very simple. We want users to write, hey, I want to do a for loop 12 times. Alternate loops must pass true and false as the first argument, and a few matrices should be passed over here and there. Each individual step is also a complex matrix operation. There's some conditionals, matrix multiplications, transposes, everything that you would expect in a problem like this. So the first thing is, the same code can be converted to Python very trivially. You don't have to do anything here. It's just the same syntax, nothing fancy. And now this works on CPU and GPU both. So I wrote some benchmark code, and I can see the GPU getting utilized 60%, which I wasn't happy with, but I haven't been able to tune it further, and I'm not a GPU engineer. It's still much faster than the CPU code, so I was happy with that. The same code works. So one thing we forgot about in this is optimizations. It was alluded to earlier in this talk that since we have a single graph, we can do some optimizations on this, right? And this is not a compiler, full compiler lecture, so I'm not going to cover all of them, but a very simple one can be this, right? So I want to spot room for optimization in this slide, right? Like let's find an optimization opportunity. And the answer is this line, where we're transposing the transition matrix multiple times. This function that we're inside is called 12 times, or like n times, 12 in my benchmark. The transpose operation, I would hope, doesn't get called 12 times because it's the same thing, right? So we can just add some node deduplication logic. And it's pretty simple. Like, this is how you write most optimizations in graphs, where you start with an original graph and you create a new graph object. The new graph is empty first. You start walking the old graph in topological order, node by node. For each node, what you do is you rewrite the node. You clone it first. Then what you do is you look at all of its input arguments. You see if those input arguments exist in the new graph that you constructed. To do this existence check, you need some sort of a signature for this node. And you can define the signature by uniquely identifying or hashing its input arguments and the operation that the node is doing, among all the other things that the node is doing. You may not want to be too strict. Perhaps you don't want to include the source location of the node in the signature so that you can merge two nodes constructed at two different places that do the same thing. Other than that, it's pretty simple. If you repeat this operation, you can actually just deduplicate nodes and you get a new graph. And we did our first graph optimization. You can cut the nodes from 148 to 105 in my example. I have some benchmark here. I noticed that the GPU code actually did not change much, and I'm assuming that's because MPS graph already identified that this was a repeated operation. There's also a secondary nature here, actually, that I correct myself. That was my initial hypothesis. Then I realized I added the profiler, and I found out that the transpose operations are not super expensive on the GPU. Finally, benchmarks. This is just the same code. It's not meant to be read. But as we saw, we can get profiling out of all of this by just a flick of a button. And the limitations of all of this, of course, is that at least the Apple AI code is partly AI generated. The Apple Metal code, this is not really production grade code. Not every graph op means something in every backend either. We did do matrix multiplication, but I don't know if it means something if you're trying to render to some limited FPGA, perhaps. Like maybe that doesn't know how to do matrix mult. And the graph is just a common parsing layer. It's not a miracle optimizer. We still have to do all of the things that you would have to do in compiler dev to make this a fully performant backend generation system. I think my experience in this, the most interesting part, of course, was to convert that LLVM code to MPS graph, which I didn't know too much about before I started. They have very different compilation and runtime syntax, semantics. MPS graph doesn't even have a compile layer, although you can take the graph and serialize it. We provided a language agnostic UX, at least for our UI users. One side wish I have in this is that this is how code looks in Python, where you just write some code and you put a decorator on this. And I wish that we had a cleaner syntax for decorators in C++, because then you could do the same things instead of calling functions, right? You need some sort of code generation capability, and you need to rename symbols at compile time, and that's just not really an easy problem. I found some papers discussing something similar. It's just not an easy problem, sadly. My wish is that you could do that, something with that annotation at the top. I don't think we can do that anytime soon. The alternative, on the other hand, is pretty simple. You make a function and then you add some get or compile kind of functions that can do that for you. It's ugly, but it is what it is. The last part, this one is a little brief. As I've alluded to before, I do care about type safety, especially when we cross serialization boundaries. So in the phase 2, we got an execution runtime object. We can recover the symbols. LLVM orc was able to do that for us. We didn't have to do any DL open and DL sim to get this, load the module and load the symbols, right? So why didn't we have to care about any type safety earlier? And the reason is that we did everything in memory. If you're in the same program space, memory space, you know you generated the code with a certain signature. So if it compiles, and as long as there's no bug, you should get the same thing back. Type safety is just guaranteed by nature of the way that we did the LLVM jitting here. Unless, of course, you screwed up the jitting. So, is this enough? I think there's two other spaces where we still need to talk about type safety. And the first one is when we actually did the graph construction, and we exposed an interface for users to reflect a function and add a reference to that function into the graph, either through Python, where they might have had an external function, or in C++, when you can just reflect a function. And inside the graph, I would like to embed information about what signature of the function did we expect. This is something that's made easier if with reflection, because now you can access the signature. The second part is at the loading and jitting time. If you do in-memory jitting, you don't care about this too much. But if you don't, then you do have the risk of loading an existing older compiled binary. As an example, perhaps you have an application that is loading 3 different modules that were compiled at 3 different times, and one of them had an older API. And because of the older API, its ABI has changed. You have no way to detect this at the simple load time, and your program might just segfault if you do that. So to solve this problem, like some simple requirements should be that any struct you have, you should be able to express the signature of that struct in some standardizable way. Similarly for functions, you want to be able to say, hey, I imported this function, this was the signature, please make sure at runtime that it's still the same signature that we're injecting into my symbol map. And this is only relevant for the first code path that we tried here, where we generated C++ from our DSL, because you can cache the .so file. In the other 2 cases, it's not relevant unless you introduce a serialization layer for the .so or the shared dynamic library or even the IR. So do we need type safety? Only if you save it to disk, and then you try to cache it and bring it later. And theoretically, you could need it in all cases. It's just we didn't need it in most cases in our talk. This is something that is very close to me. I've talked about this 2 years ago at CPPCon and at CPP now. I tried writing a paper on this, which I'm trying to revive now as a part of this whole effort to write this code, where what you can do is hopefully we can standardize a way to talk about the ABI of a function or a boundary type that's on the API boundary of your program. It's very simple. You just have to recurse over a bunch of different members of your type. You have to serialize everything about them into some object, perhaps a hash, perhaps a JSON, perhaps a map. And you just do it diligently enough, and now you have a true signature that can describe each type that you have. So using this, if you had some code like this that imported a bunch of functions, what you could do is, instead of asking users to do something like this, where they say DLSim, they jitted their code, and they just assume that the final pointer is of that type. If it's not, then great, good luck debugging that segfault. This is the current situation. So maybe I tried playing with a few APIs of what the end result, like a good end result, might look like. There's a way to do that with some sort of an image shared object. Maybe you want to add some reflection there. Maybe something with imports as well. I feel like the one I like the most is something like this. I realized that maybe the symbols that we expose in our program at the end could have a way of being exposed as a map instead, or a list instead. This provides some future ABI breaking capabilities to your ecosystem, because as long as you do this both at the symbol export time and the symbol import time, life is good. Because what I did here is I said, hey, if you want to look for the compute symbol, you can either look for the compute symbol, or you can look for something called compute symbol map, which is of a certain type. That type is just a list. You loop over that type, you check which pointer in that type is the correct signature that you want. So if someone wants to do an ABI break tomorrow, where they converted that double function, the compute function that consumed the double, from double to float, they don't have to go and update all their callers. All they have to do is add another entry into that symbol map. And now the ABI of your software is theoretically changing, but downstream consumers are not going to crash because of the change in the signature here. The logic is pretty simple. You load the compute map, you loop over it, and as long as you have a signature, you can do something with it. Hi.
So instead of adding an extra level of indirection, have you considered just mangling the name akin to what C++ already does?
Mangling the signature?
Mangling the function name.
But like you mean, okay, yeah, so you can mangle the function name, but then the problem is that you don't provide a way for the user to load the older one. They still need to be able to.
Well, if they need, that's how overloading works, right?
Oh yeah, okay, sure, yeah, you could mangle. Okay, that is an interesting point, and that would It will not be able to give you a clean error if you cannot find any of those, but yes, it would work. So that would get rid of this indirection actually. It's a valid point. Yeah. The end goal is just using these signatures, we can actually make this ABI boundary at the end of your program safer. And that's something we can only do with reflection now. It's an easy path. We can make, so I had this point about slight load time hit, which would go away if you mangle the full function name, yes. It's perhaps a solvable problem, theoretically, pending various things. You can notice the number of softeners I have. This is just a POC. So I guess to conclude, where does all of this belong, right? Like, I think the DSL or the IR and everything, this just belongs in libraries. This is not really standardizable stuff, right? Maybe some boundary description for structs and functions that we're using. There might be more room to standardize those. Some annotations that can make the source-in of these JITted functions easier. And lastly, a typed DLSIM, perhaps. So I guess, hopefully we covered a lot. We designed a DSL. We started with the graph-based DSL. We converted it to C++, converted it to LLVM, even to Apple MPS Graph. And we could load it and run it. We could profile it. We could inject profiling into it on demand. So hopefully we all learned something about writing runtime DSLs, also known as programming languages. All right, that's all. Thank you so much. Right? Hey.
First, thank you very much for this amazing talk.
Thanks.
I have a similar issue to the one that he talked about with the mangling and the symbol table.
Yeah.
So when you call an overload set, sometimes there is not exact match between the arguments and this function signature.
Yeah.
Like you can have casting, like
Yeah.
remove const or like
Yeah.
conversion and stuff. I was looking for a way to solve it and I couldn't find it. I'm wondering if you.
So I think one way to do it, if we don't do the mangling, if we had a symbol map, we could loop over all the signatures, find the closest one, and generate a runtime cast for it, like a runtime wrapper for it. But you would need a runtime symbol map for that. And it would be complicated because you would have to enumerate which types can be mutated, right?
Yeah.
So like maybe if the user removed a const from something, that shouldn't ideally break the ABI. That said, your code would have to notice that, okay, if the const is mismatching, then you just let it be and call that function anyway. But this would have to be done on a case-to-case basis for all of these castable/safe ABI breakages.
Yeah, thank you.
Okay, I guess.
So you touched on a couple of topics of compiler construction, that is fine, but the essential part seems to be that you create executable code and are able to insert it into your program at runtime, is that right?
Yes.
And this is the essential part. So how do you actually do that? Did you say that?
So the simplest or the most production grade way of doing that was the LLVM org library.
Okay, so LLVM org supports this?
Yes, and it does it all in memory for you.
Yes.
So you're kind of bypassing a lot of potential like foot guns because you tell it that, hey, here's some IR, and it does the whole jitting in memory and gives you the function pointer in your own memory.
Okay.
Yeah.
So you talked about some of the graph optimizations.
Yeah.
What does that do that LLVM's like built-in common sub-expression elimination doesn't?
Well, in my case, it didn't eliminate the, basically, it did not lift. So we had a matrix transpose operation that was inside of the for loop. But part of the whole thing is that that function is an external function. So LLVM will not treat lifting that transpose out of that for loop as a safe operation because it could have effects.
Did you try seeing if you could tag it appropriately?
I did not.
Correct attributes on it.
I did
so
not.
LLVM understands what it does.
Once you have LLVM, you have all the optimizations for free.
Yeah.
So there are very many.
Yeah, so I did not try to tag that. Yeah. So that would be If you tag it as something that is a pure function, perhaps it would be able to lift it out of the loop. Yeah, right?
The attributes get fairly complicated, but it should be able to understand.
All right, I will search for something like that.
So that you can do cognitive expression coordination more aggressively.
Yeah, I'm assuming that it can figure out most of the things. That said, I don't know if I can think of an example on the fly which would be easier to do on the graph than the final lowered LLVM code. Perhaps it's something with vectorization. No compiler is very good at vectorization anyway. Anyway, yeah. Right? Thanks everyone.